Okay, so this video is going to be on transformations of quadratic functions that are currently in vertex form. And the vertex form, okay, if you see up here to the left, is going to be f of x is equivalent to a, which is some multiplier of the quadratic, okay, times the x minus h squared, so this is the perfect square, plus k. So a couple of things we need to note here are, okay, what do these things mean? So first of all, a, what does a represent? A is going to be the quadratic growth multiplier, and I'll talk about that in a moment in case you wanted to graph these, and I will demonstrate how you would graph this. So in case your teacher doesn't only just want to know what the transformations are, they actually want you to graph these things. So then, okay, we have h and k, which is the translated vertex from 0, 0. So the original quadratic function went through the x-axis and y-axis at 0, 0, which is important because all translations are on a graph going to be talked about from 0, 0, okay, the origin of the axes. The other terms I'll be using in this video are going to be, I'll talk about stretching, I'll talk about being compressed, and I will talk about my translations. And my translations will be, much like you've learned back in what I teach my 7th and 8th graders, is it's either right, left, up, or down. So translations on a coordinate plane go right, left, up, or down. If you do two of them together, that's what creates the phenomenon of something looking like it's moving diagonally. So let's get into a problem really quick. All right. So this video is going to be if I have a stretch compression and do I have a shift left and right or up and down. So I'm going to put all of the transformations in one problem so you see how they all work together. So here we go. Let's get at it. So I'm going to get rid of this information here and we're going to talk about it. All right. So a couple of things we need to have a discussion on is this. So the problem I'm going to use is f of x is going to be equivalent to 1/2. Open your parentheses, do x plus 1, the quantity squared, and then I'm going to do minus 4. All right, so for this particular quadratic, I just want to talk about what are the actual things that have happened here, okay? So what are the transformations? So A, okay, as we talked about before, that is your growth multiplier. So here's the deal, okay? You need to think about, okay, the original function, the original quadratic. So the original quadratic looked like this. It went 0, 0. It went 1, 1. You go over 2 and square that. 1, 2, 3, 4. Okay. Over -1, square a negative term, you're still going to get a positive. Square -2. Okay, so you get these points. So what you have here is something that's beginning to look like this. So I'll draw this a little bit more. Okay, so I've got this graph that looks like such. All right, and what we're going to do is we're going to alter everything. And what you need to know is that after the fact, okay, after all things are done, after I've done everything to the quadratic, what I'm simply going to say to you is, okay, we still need to be thinking about this quadratic at its kind of specific points. And these are called, like, if you want to call them critical points, 0, 0, okay, is a critical point. 1, 1 is a critical point. -1, 1 is a critical point, okay? And what I really want to focus on is just the outcome. So 1, 1, 4, 4, 9, 9. So those are the values that I really want to focus in on because I want to talk about what does the multiplier do, okay? And what the multiplier simply does is it takes whatever those current critical values are and it's going to directly multiply them. Okay, so I'm going to take half of whatever my original quadratic will do. So if I'm multiplying by 1/2, what it's doing is saying, hey, take the output. And the reason why it's the output is because this multiplier is outside of the squared term. So what I mean by that is if I take these parentheses away, it's really like I'm doing 1/2 times x squared. Okay, this is my function, okay, of x squared. All right, so this is the end game. I'm going to do this after I get an answer. So this thing here and these thing here, they want to produce the same thing, okay? They still want to produce this 1, all right? So what I'm going to do is multiply it by 1/2. And what that simply tells me to do is it says take all of these points and take half of them. So if this value here, okay, is now a half, this 4 now becomes 2, and this 9 now becomes 4.5. 0, we take half of 0, you're left with 0. So it's directly on top of that point. So what we start to have forming here, okay, is if you notice in green, all right, all of these points, all right, are going down. Okay, they're all going down. So what I mean by that is, okay, is that that's where these terms of stretch and compress come into play. So what is this 1/2 actually doing? It is what we call, think about a compressor, okay? A compressor pushes down on things. So this is actually pushing these points down. So this value out here is going to determine whether you push down or whether you push it up. Now, the critical number, the critical multiplier is A if it were 1, because to multiply by 1, okay, it's an identity property, which means if I multiply by 1, nothing changes. So things don't begin to change until after 1 or before 1. So if I have an absolute value, so if you take the absolute value of A, so whatever that value is, whether it be positive or negative, if the absolute value of A, okay, is greater than 0 but less than 1, all right, you have what we call a compression. All right? If you have an absolute value of A, okay, that is greater than 1, all right, what you will have here is you will have a stretch. All right? So, and it may seem awkward, but it has to do with the fact, if we're talking about, okay, going towards the x-axis. So what this value is doing, it's affecting whether the points go up or down, all right? So this multiplier, again, what I want to point out is affecting whether these points are actually going up or down. And that's kind of important because that's where the idea of stretch comes from. Stretch would be taking your point and pulling it apart. Think of a rubber band, pulling it apart. You're stretching out the rubber band. So if I pull the point farther away from its original position, in retrospect to the x-axis, or to its vertex value, I should be saying here, then I'm stretching it up, okay? So what I want to also talk about is, because some teachers talk about it different because it's, apples to eggs, I can also talk about this value actually stretching. So what do you mean by that? You just told me it's a compression. So not to confuse you, okay, some people like to talk about how this stretches away from the line of symmetry of a quadratic. So you have to figure out, what does your teacher want as a response? What are they looking for on a test? You have to figure out the pattern of the questions they're asking in class. But to be talking about this specifically, this multiplier truly and definitely should be being talked about as being a compression towards the x-axis or a stretch, okay, because that's what this does. This number affects whether it goes up and down. It doesn't affect left to right, okay? It affects whether that point goes up or whether that point goes down. The graph will look compressed towards or stretched away from the line of symmetry based on the movement of that point, okay? So we're literally talking about what are the points doing in correlation to its minimum or maximum value, okay? So now we go back, all right? So that is what the A does. So in this case, if I had to talk about it, okay, I would say that this graph, as of right now, has a compression. Okay, so that is the first transformation, and it's a compression. Okay, so the next thing I have here, okay, are there any translations? So this is where we go to back to this, right? So you see this quadratic function, how it originally was centered at 0, 0. So to figure out what happens here, okay, I want this to go back to doing 0 squared, okay? So I want to do 0 squared. So how do I turn this thing into 0? Well, very quickly, if you take a look at this, and if you were to do x plus 1 equals 0, you can go ahead and solve for what the translation will be. So we're solving for x, so we're solving for a movement left to right, all right? So therefore, I get x is equivalent to -1. So what I have here is if x is equivalent to -1, all right, what we have is negative means shifting left, and the 1 will tell us the value of that. So I have a translation, okay, left 1 unit. All right, and you can do this for every one, because the nice thing about something in vertex form, and what you'll begin to learn the shortcut of, is everything in vertex form inside these parentheses, the coefficient of x will always be 1 if done correctly. All right. So this is talking about if I have +1, notice how I got -1. So this is an important idea, because if you want to figure out the shortcut, when you set this equal to 0, what you're actually doing to find the x is you're taking the opposite of this value. So -1 for both sides, you end up with -1. So hence, if you look at the sign in there, the shift left or right will always be the opposite of the value that's in there. So now we go back on to the next thing. Well, what does the k represent? So what does the -4 give to me, all right? And again, we've already talked about the point being stretched up or down, okay, via multiplier. So the last thing I have to talk about is this. What does this k value do? Well, if it's -4, so let's talk about this very quickly. If this thing originally was centered at 0, well, what does -4 do? Well, if I started from 0, -4 will take me down the -4. So what this value does is a direct comparison. It literally tells you directly which way to go. It is outside of the function. So after I move it left or right, or stretch it down or compress, or stretch it up or compress it down, I then say, hey, take those points and literally take 4 off of them. So the outcome it gets then, right, because we're talking about y values, the y value will then go down 4. So whatever this is a direct correlation to whether your point moves up or whether it moves down. Minus means moves down. So what I get here now is I have a translation left 1 unit, and in this case, down 4 units. All right? And then what you have there, okay, is all of the transformations that happen to this graph. So let's talk about another one. The teaching lesson is over. So now we're just going to go to, let's do a problem and talk about the transformations, and then from there we'll go ahead and graph it. So here we go. All right, so the function we're going to now talk about is going to be 2x, or 2 times the quantity of x minus 3 plus 1. So I want to know what the transformations are. Again, one of the things I talked about in the teaching lesson of this video, so if you want to watch the beginning part, if you skip through it, is going to be this value. What are the values going to be that either pulls the point away from the x-axis or moves it farther? So here we go. This value here is a 2. So what that is going to do is it's actually going to stretch the values, okay, farther up. All right, so it stretches them farther up. All right, and then we take a look at this value. Well, if you want to, again, you just simply set this interior equal to 0. You get x minus 3 equals 0. And now when you solve for x, x will tell you what your shift was. Well, x equals 3. So again, shortcut to this is you're literally just taking the opposite of the value that's on the inside. So what I have here is a translation to the right. Okay, translation right, 3 units. And then we also talked about k. Okay, k is also going to tell me what my direct, so this is a direct correlation. It tells me whether my points then get all shifted up 1 point or down 1 point. Because it's positive, I also have up, so 3 units to the right, and then up 1, and then you have literally all of the transformations for this particular graph. Now, in the next example, the only thing that I have yet to talk about is going to be the negatives. So first off, let's talk about this very quickly, and let's talk about how we would graph this, okay? So first off, okay, so the original graph looks like such. 1, 1, you go over 2, up 1, 2, 3, 4. So I'm squaring any value on the x. So 1 squared 1, 2 squared 2, 3 squared 9, okay? Negative 1 squared 1, negative 2 squared 4, negative 3 squared 9. So I'm going to leave those there in points because I don't want you to confuse that this is the graph that I want. The transformations are this. The transformations stretches it, okay? It doubles it. It literally is going to be a direct correlation. So take all of those points that they currently are, and you're going to double their distance. But the problem is I don't want to double them from 0, 0, okay? I want to double them from the translation of h and k, because now what we need to keep in mind here is that you see these points here, 3 and 1? That is the translation of this point. So this point is moved 3 to the right, so up 1, 2, 3, okay, over 1, 2, 3, and then up 1. So I'll graph that very quickly in red. So 3, 1. So there's my point. Now, if this were the actual, okay, if this were the actual graph, I would go from here. I would just mimic this graph. Okay, if I only moved it and did nothing to it, I would go 1, 1, okay? I would go over 2, then square it. Over 2 squared makes it up 4, okay? Over 2 squared would make it up 4, okay? So what I've got right now, just so you're aware and just so you can see it, all right, is that I've got, all right, this graph just moved over then up, okay? So everything is over 1, up 1, okay? The final answer to this, okay, with the stretch in all of this, is going to be that all of these points, except for this one, this is the only one that's going to stay put, okay? Everything else is going to move up twice its amount. So this value here, you double it. So instead of going up 1, I'm going up 2. Okay, so up 2 here. So let me get rid of this. So up 2. See this point? As opposed to going over 2 and up 4, I'm going to go over 2 and up, not 4, double it, 8. So another 1, 2, 3, 4, and I'm left with that point. Okay? So I hope you're starting to see these transformations a little bit. Instead of going over 2, up 4, I go over 2, up, instead of 4, go up 8. Okay? And what I've got now is I've got this new graph that comes in that looks like this. So now, that it would be graphed, and what you can kind of see is that this graph looks like it's a little bit pinched in. So that's why some teachers talk about these being a compressed graph. However, you need to remember that we're talking about what did that point do after the translation. And this point was pulled farther up. Therefore, it is a stretch. So it's the opposite of what you may think of. I know you look at the graph and go, but the graph is skinnier. That is true. But the graph is skinnier because you took this point and pulled it up. All right? So one last one here that we're going to talk about is what happens if A, okay, was not something nice that we have. All right, and let's talk about A. All right, so here we go. For A, we're now going to do the last function of -2, parentheses, x plus 2, the quantity squared minus 3. All right, so here we go. So first things first, if you're in the teaching lesson, it is the absolute value of A that is going to determine what I have here. Is it a stretch or is it a compression? So the absolute value of A, so what is the absolute value of -2? The absolute value of -2 is 2, all right? So therefore, I have a stretch. So this, again, is going to be a stretch. All right, that's the first thing I would notice here. So I'm going to stretch my point away farther. Now, before I take the absolute value, notice that before I did one that was positive. The negative, since it's a negative multiplier, all right, what it's going to do is it's going to flip this graph. It's going to reflect the point down, okay? So this point, this thing here is also going to have, okay, depending on how your teacher wants to talk about it, how they want you to answer it, you would say it has a reflection about y equals k. So reflects, okay, reflects across y equals k. So what you have there is it's going to reflect across wherever your vertex coordinate is. You draw a line straight across, and everything is just going to reflect down across that. So that is the formal way of writing it. Your teacher may just be cool with you saying flip. So you just have to find out what your teacher is good with. All right, so there we go. If negative, it flips it down, which means we have a reflect across y equal k. So in this case, it would reflect across y equaling, and k in this case is -3. All right, so the next thing have, okay, so obviously we do have an h, we do have a k, so our vertex has also been moved. Remember, if we set this middle thing equivalent to 0, I get x plus 2 equals 0, therefore x equals negative 2. This value right here tells me my translation, so my translation for x, so the translation, okay, is left 2, and then this is the direct correlation, comma, down, all right, down 3. Okay, so we have a opposite correlation, and then we have a direct correlation for translations, whether it's up, down, right, or left. So let's say your teacher had you graph this. So the first thing, again, you would need to note is that you always start with the vertex, okay? So move your vertex first, then talk about stretching your outcomes from there. So I'm going to take my vertex, which is normally centered about 0, 0. I'm going to move it left 2, and then I'm going to move it down 3. 1, 2, 3. So there it is, yes? All right. So normally, again, I'm going to put up here in red. Okay, normally I would go over 1 value, square it, and I'd get up 1. Over 1, up 1. Okay? From here, I would then go over 2, square it, go up 4. Over 2, up square it, goes up 4. But the problem is I don't just have something by itself. I've got a multiplier. And what the multiplier is telling me to do is to multiply it by negative 2, right? So I don't want these points going up. I'm going to want them going down, all right? And not only that, I'm going to stretch them. So as I move them down, I'm going to stretch them farther away. And the amount I'm going to stretch them by is double the distance they would normally be away. So in this case, all right, this is positive. What I want for negative, get the final graph of this, is I would go over 1, and instead of going up, I will go down 1, but the multiplier tells me to double it. So whatever that multiplier is, I will double it. So if this is go down 1, I go down 2, okay? So over 1, down 2. The next thing I would have here is if I go over 2, normally you go down 4, but I'm going to double it. So instead of going down 4, I'm going to go down 8. So down 1, 2, 3, 4, 5, 6, 7, 8. And plot my point. Plot my point over here, over 2, down 8. 1, 2, 3, 4, 5, 6, 7, 8. And what I now have is 5 points. And generally, most teachers are only going to require you to plot 5 points before you go ahead and draw your smooth curve in there. And what I've got is all the transformations plus some graphing here for you, okay? So I hope that helps with whatever you're doing. Again, if you like this video and what I've talked about here, please hit the little like button. And it's not for me, I could care less. It's just to help out other people, because if it doesn't get a lot of likes, when people go to search, they don't get to see it. So if you want to help out a fellow math person who wants to get some help on this, hit that like button and subscribe. Appreciate it.